This mini lecture is about orbitals. Well, first of all, let's talk about what orbitals actually are. An orbital is really just a region of space where you can expect to find an electron. And this would be a p orbital here, so you'd expect to be able to find the electron in this region. And this would be familiar to you. This is the energy level diagram. You can have 2 electrons in each of these orbitals, and when you get up here you put them in one at a time before you fill the rest of them up. Here's what some atomic orbitals look like. You've got your s orbital, which is a spherically shaped orbital where you can find the electrons around the nucleus. The s orbital is just basically a bigger example, a bigger version of the 1s orbital, but it has 2 parts to it that have different phases associated with them. And you've got the p orbital, which has different phases as well, top and bottom. And you can take a look at the shape of the p orbital. It's dumbbell shaped. And we're going to have 3 of those, one for each axis, x, y, and z. Alright, let's take a look at why orbitals are important. If we take a look at garden variety carbon, we've got 6 electrons. We put them all in the orbitals, 2 here, and then 1 here and 1 here, obeying Hund's rule. Now if we look at this, we might think, well, we've only got 2 unpaired electrons, carbon can only bond twice, right? Well, that's not true. We know that carbon can bond 4 times. Now, it's further, if we take a look at something like this, we know that these 4 bonds are of equal length and equal strength as well. These lines here, this dash, it means that the hydrogen's going into the screen. This wedge means the hydrogen's coming out of the screen. But the point here is that this carbon has 4 equal bonds, and that's not what's predicted by this energy diagram. So what we need to do is be able to explain how we get, say, for example, 4 equal bonds out of something like this. And the secret to that is in hybridization. Alright, let's take a look at a hybridization example. If you wanted to find the reason for why we get 4 equal orbitals, this is the reason. Let's pretend that you've got 3 yellow containers here, and 1 container with a blue substance. We all know that when we mix blue and yellow we get green. So what we've done here is we've taken all 4 of these orbitals, the s and the 3p orbitals, and mixed them all into one container. And then if we pour them all back out, what we've got are 4 containers that contain 1 part s and 3 parts p. So that's it. That's what hybridization is. And you're always going to get as many hybrids here as orbitals that you mix. So if you mix 4 orbitals, you're going to get 4 hybrids. And you can see each hybrid is 1 part s and 3 parts p. That's why this is green now, because it's a mixture of blue and yellow. So it's going to be each one of these is a mixture of 1 blue and 3 yellows to make the green here. Alright, let's look at the same website again. We can go back to here and take a look at some examples of hybrid orbitals. What this will do is it will go through and explain how we're getting 2 hybrid orbitals here using 2 hybrids, using 3 hybrids for this one, and using 4 hybrids for this one. So if we wanted to take an s and a p, we would combine them together and we'd get what's called an sp hybrid. We actually get 2 sp hybrids. So there's your carbon right there. Now if we take an s and a p and we combine them, what we're going to get is 2 hybrids s and p. And each of these hybrids is 1 part s and 1 part p. So they're half s, half p. Now notice also that there were 2 p orbitals left over. We didn't touch those. So when we take all these orbitals and we combine them, here's what we're left with. We've got the p orbitals here and the 2 sp hybrids right here. and those two sp hybrids are 180 degrees apart. This explains why here the bond angle is 180 degrees. That's all got to do with the fact we're using two sp hybrids on this carbon atom right here. So here's another view of it, but you can see everything is 90 degrees apart, and that makes this 180 degrees from one sp to the other sp. Now if we want to explain three things connected to the carbon, then we've got to use sp2 hybrids. Now sp2 hybrids are formed from 1s and 2p orbitals, so that gives us three sp2 hybrids. Each of these hybrids is 1 part s and 2 parts p, but they're all the same energy, as you can see here, so we're going to have one p orbital left over. Join them all together, and here this explains why we're getting 120 degree bond angles for this one here, because those sp2 hybrids are 120 degrees apart. And you've got a 90 degree angle to the leftover p orbital. I'll explain what happens with the leftover p orbital later on. Now if you want to explain something like this with the 4 bonds around carbon, then what we've got to be doing is taking 1s and 3 p's and creating 4 sp3 hybrids. So that explains how we're able to get 4 equal bonds for something like methane that I was just showing you earlier. There we go. And the bond angles here are 109.5 degrees. This is a standard tetrahedral bond angle. There we go. Now as I said, you've got sp, that's 50% s, 50% p, and you've got sp3, which is 25% s and 75% p. That's 1 part s and 3 parts p. So you can see you'd expect these to have more p character, that is to be long and thin, and you'd expect the sps to be short and fat, and that has a direct effect on bond length as well, which we'll talk about later on.